Ladies and gentlemen, also for this problem, you could have done the collapsed equation. I mean, you can choose. I will provide both, whatever is more comfortable for you. All right. There is another thing to consider as far as reactants go. So remember, I had communicated that the most common order is first, then second, then zero. And once you know the order of a reactant, then there's a bunch of stuff that you can apply about it. So I'm going to take these 3 whiteboards and make a first order board and all this stuff. All this stuff that we can apply, then second order and zero order. You're invited if you want. I definitely have white. If you would like to jot down what I'm jotting down. Oh, not only do I have different color, I have yellow. Won't that stand out? Not that you. A piece of come out of your seat and go. You do not have to get a yellow sheet of paper, but you're free to. If you get a yellow sheet of paper and you think, what is she doing? You don't have to write on it. Okay. So as soon as you know that your reactant is first order, write down what you want. Okay, what does that mean? My rate law is going to look like this. Okay. I know that we are amazingly talented. I have no doubt of that. Can I share with you, there are some test creators with the College Board that worry about using generic A for the reactant, that when you're actually given a formula, you won't know what to do. I think that's hogwash. You guys know that's just generic. If you're given a reactant, it just is no longer generic. Yeah, I know we're good on that. All right, so I'm going to keep using A because we got that covered. All right, so if you would graph concentration versus time, well, the curve we expect. However, if we integrate this, we get natural log of A equals negative KT plus natural log of A. Got it? And so the way that we can confirm first order is by graphing the natural log of concentration versus time. If we get a beautiful straight line, we know it's first order, and the slope is negative K. Also, if you feel more comfortable, with, I don't know what to call this, the collapsed version. All right, there's another thing that I want to add to that. T with a little subscript of 1/2. One thing that is useful is to evaluate on the very next page, page 10 in our unit packet, half-life. Half-life is the amount of time it takes to react half of your quantity of reactant. Well, yeah. So if we start with 100 grams, how long does it take to react away half of it? But we can keep going from there, right? And on and on and on and on. So this would be the first half-life, the second, the third, and we keep going and keep going and keep going until 0. Okay, well, what is super neato about a first order reactant? All right. Natural log of A equals negative KT plus natural log of A naught. All right. Well, if I want to find half-life, I want to know, I'll go ahead and use those values I put up there. When I have 50 grams, now I'm just going to use 50 generic, because that's not grams, it should be molarity, of course, is negative K. Well, I'm looking for half-life plus natural log of 100. Well, if I rearrange this into the collapsed version, natural log of 2 now is 0.693. The half-life of a single or first order reactant can be found through that equation. 0.693 divided by K equals my half-life. That's what I want to add here. All right. Now, this is a significant arrival. Now, why? Half-life is constant for a first order reactant. Half-life is constant throughout the reaction. Ava, could you choose a time amount? So could you pick a number between 1 and 50? And second minute? Okay, so let's just say that this half-life is 50 seconds. Well, guess what? The next half-life is going to be 50 seconds. And the next half-life is going to be 50 seconds. That is particular to a first order reactant. If you don't have to turn back to it. If we look, in fact, at this set of data in the previous problem, okay, it took us 100 seconds to react away half. Well, look at that. Oh my golly, Gearhart. Took another 100 seconds and then another 100 seconds. I'm sorry, I got thrown off by the 0, 50, 100, and then we started skipping 100s. First order reactant, constant in its half-life. All right. How can that help us? Well, could you please turn to page 12? No, 2 seconds. I know. 21. I'm sorry. Page 21. Okay. We'll warm up to the problem solving. So, what about 8? After 3 half-lives have elapsed, what fraction of the original reactant remains? So, go, sir. Are we good on that? Excellent, excellent, excellent. Okay. Let's go with 7. Could I ask you to read that, please? Oh, phooey. This asks us to rely on another. All right. Pause. We do. I'm so sorry. I can't find my one key. It's Critten's fault. He's not here today. I'm so sorry, ladies and gentlemen. I cannot find. I brought my packet. Oh, instead of 7, I'm so sorry. And then we'll come back to do one on this page. Okay. What if you have a reactant? So we'll say this is a Gearhart example. And the half-life is 20 minutes. And let's call it reactant A for Atlee, not just generic. All right. So find K and B, how long for reaction to be 85% complete. All right. So if we want to kind of set the stage, maybe you're a chemical engineer and you know it's a first order reaction and you need to refill a vessel with reactant when your reaction just had 15% of the reactant left. Okay, so we need to figure out when that needs to happen. Finding K, easy peasy. So first order, as soon as we know it's first order, all of this is fair game. All of this. But of course, we're dealing with half-life. There's how we get our K. Yeah. Oh my gosh. They're hurt. Please forgive me. Oh, how embarrassing. I rearranged improperly. Okay. How do we find B? David, would you mind being our second answer? Our second thought? Right. Do you mind? Because we know you know, but I would love to hear someone else. Because Damien, I wonder if we think, oh, Damien's going to answer, so I don't have to think, or so. If you don't mind just being patient, thank you. Go, sir. Mm-hmm. Are you positive about this? Sure. Or couldn't we say, well, I'm going to choose easy numbers. I don't have to move the decimal as long as that's okay with you. Well, if 85% complete, if we start with 100, but you could do one, you could do any number. Well, I want to know when it's 85% complete. So I have my reactant would be 15. Huh? Then divided by the 0.0347. And it will be 54.7 minutes. Damien, what were you thinking, sir? Great. Yeah, that's what and you wouldn't have to collapse it, but that appeals more to my thinking. Questions? Okay. Do we have to memorize? No. But we just have to know, okay, what applies to first order? Why would we ever do this? When do we do that? And then how do we apply these equations? All right. So can we please find our way to page 13? Okay, so your book shows you how we take a second order reactant and integrate it. So this is our equation for a second order reactant. So if I go back in my paper, so do a different color. Second order. Now I'm going to set mine up. You choose to write whatever you'd like to write, just like I did the first order information. I want to make sure that I'm distinguishing separate information. All right. Second order, our rate law. Okay, so that means if I would graph concentration of A versus time, I'm getting the curve. And if I would graph natural log of concentration versus time, we're going to get a curve. The integrated rate law for second order, 1 over A is equal to positive KT plus 1 over A. So if we would graph the inverse of concentration of reactant versus time, positive slope, and the slope is our K. If we would do the same thing that I showed you to derive the half-life equation, the half-life of second order, you will be given these. We don't have to memorize. 1 over K A naught. Okay, so Maddie, as the reaction proceeds, if our reactant is second order, now this would be like the original concentration, then whatever you would have after the first half-life, that would be your next A naught. As the reaction progresses, how does your half-life change if it's second order reactant? A fourth? So if I just pick 1 mole, okay, to find this, it's 1 divided by K time. All right. Well, then it'll be 0.5, yeah? So 1 divided by whatever K is, that's 0.5. And then it'll be 1 over whatever K is, 0.25. And then divided by 0.125. And then, so as the reaction goes. So for the first order, right, your half-life is constant. 50 seconds, 50 seconds, 50 seconds. The concentration has no impact on half-life. But here, concentration does play a role. As the reaction goes, Maddie, how does the concentration of reactant change? So, is it getting smaller, smaller, smaller? So what's going on with our half-life? Yeah, so your half-life increases in time. All right. So why don't we just go ahead and go to 15. All right. So our next most common zero order. So formatting, just like it was above. Rate equals K. A to the 0th. Okay. Now, how on earth could we ever have a reaction where the reactant concentration has no role on the rate? There must be something else going on. So in our gasoline fueled cars, yeah. So we know that the combustion of gasoline produces some byproducts that don't necessarily want to add to our atmosphere. And so, oh gosh, use your imaginations, please. You have your car engine. Oh, good golly. That's your tailpipe. All right. And then there's your muffler. Oh gosh. I don't even know. Anyway, just please use your imagination. So there's, the combustion, which pushes the piston, which turns your wheels, great. But we get all these byproducts. Well, that is channeled through your muffler. And your muffler has a bunch of substances that coat the inside. So when the nasty stuff, like carbon monoxide, passes through, it will come into contact with some of that substance and get locked there. And then it doesn't pass outward. Or it gets locked and then chemically reacts. And so then we're releasing oxygen and then the carbon will be there. That's not what happens, but I'm just saying. Other gases and so on. So it's not based upon the concentration of the carbon monoxide. It's based on the amount of surface that's available. So in this case, zero order. Okay, so if we keep taking a look, so if we would graph concentration of A versus time, then because the integrated rate law for zero order, A is equal to negative KT plus A. So if we start out with linear, you know it's zero order. For the others, we would get a curve. And we see the half-life. For zero order, as the reaction proceeds, our numerator is decreasing, and so our half-life will decrease as the reaction proceeds with zero order. All right. So page 18, please. No, false. Page 17. Okay, we'll just talk through this. Just talk through this. Okay, so if you were given this information, here's our reaction, a single reactant, and then Sophia came, did the reaction, and measured after 15 seconds concentration, after 100, and so on. All right. So they're asking us to graph to determine if it's first order or second order. Well, then what we need is the natural log of concentration versus time. And then, of course, for second order, the inverse of concentration versus time. So here are our values. I created them, and they're on the next two pages, the graphs that we would get. Okay, so Grace, this is natural log of the N2O5 versus time, and this is the inverse. So what is the order of our reactant and why? The next one, so I want to make sure I apologize that I believe I failed at completely explaining. Please forgive me. So imagine Sophia collected this data, because that's what we measure in lab, right? Time and concentration. If we would graph, I mean, we can see that, oh, okay, no, it's going to be a curve. Yeah. So we took that data and first I did natural log of concentration and then graph those. And then inverse versus. Okay. So when we get a curve, it just says whatever would be confirmed if it was linear is not that. That's all it tells us. But if it's linear, it's first order because what? What would be our reasoning? Go ahead, sir. What equation?
A equals K times T or negative KT plus natural log of A.
Which matches with honors the integrated rate law or a first order reactant. Go ahead, sir. Obtained. Yielded. Oh, we could even just say first order, because linear relationship when this is graphed. I guess I was trying. Obtained. Yeah. Is graphed, which matches the integrated rate law, or which matches natural log of A, just as Damien said, equals negative KT, et cetera, for first order reactant. So we have to know why this graph confirms that order. Easy. Okay, turning it over to you. Can you answer 5 and 6? This should take us 2 minutes. You can definitely check in with your neighbor. Are we set on 5? Right? These are all, no, these are supposed to be brackets. Sorry about that. So these are all concentration versus time. So we just have to know, like, okay, what do we need? What exactly do we need graphed to confirm that order? Well, that won't confirm first or second order. It just tells us it's not zero order. Yeah. We would need natural law of concentration versus time to be linear. Yeah. Okay. How about 6? Or still working on it? Okay. Think. Do you notice, amazing students, that you're not just given the curve, we're given actual values on our X and Y. Now, if that happens, not always, but I would think, oh, someone went through the effort to actually scale this. I might need those numbers. Okay, what's our answer? Of these 4, is that too much pressure? I totally get it. Dylan, what are you thinking? Between the 4. I'm the teacher. I should just choose. Okay. I do believe I saw Rishi's hand first. Go. Explain. How? So remember, half-life is constant for a first order reactant. And is that true here? So, and again, guys, look how nice. They started, whoever did this, with 1 molar. So we just have to see, okay, how long did it take us to go to 0.5? 50 seconds. And then to 0.25, another 50 seconds. First order. All right. So let's get to that. This is our last problem. So let's look at number 10 on page 21. Remember, I was going to have us do number, so I don't know what I was thinking. All right. Radioactive substances react or decay as if they are first order reactants. So carbon 14. All right, so I know as soon as I see first order, all this applies. I'm given my half-life. Oof. So Isaac comes across an ancient bowl, and when analyzed, it has 6.29 disintegrations per minute per gram. Huh? Living wood has 15.3 disintegrations per minute per gram. Do we understand how radioactive materials, what that means? Isaac, do you mind explaining? What does it mean to decay? It can, or it could lose energy. So what we believe makes an element radioactive is it has a super heavy nucleus, or the ratio of protons to neutrons is not 1:1. Carbon 12 is the most abundant form of carbon. 6 protons, 6 neutrons. Carbon 14 is the radioactive, where still 6 protons, but we have 8 neutrons. And so bits of the nucleus will be released. And what can come out is a neutron. What could be released could be an electron. What could be released is a positron or a positive electron. Is that not a crazy thing? It also can release nasty stuff like gamma radiation or all kinds of stuff. But the deal is, in a nuclear reaction, the element converts often to a different element because we're changing the nucleus. Carbon 14 at one point changes to nitrogen. Okay, so this is, if it was living wood and you just made the bowl, if we would measure the carbon 14 in something that was just alive, this would be the concentration. Isaac's bowl is that. Remember the how long would it take for 85%? Okay, half-life. Okay, we're given our half-life. So to find how long did it take to go from 15.3 to now 6.29, we need to know K. We find K here, plug it in, there we go. And if I'm not mistaken, the too many papers, too many papers. Oh, for heaven's sakes. Well, That's how we would problem solve. Can someone find the answer real quick? Oh, we have to find K first. No sweat. Oh, out of time. You're so happy, but I'm not. All right, we'll pick up tomorrow.